Welcome back to this course on multi-core systems. The topic of this and the next few lessons is cache coherence. How do we ensure that shared data that is stored in multiple local caches is consistent? That all processes see the same value? In this lesson I will first illustrate the cache coherence problem and then give some properties that a coherent memory system must fulfill. I inform you of the literature this lesson is based on. It's based on section 5.2 of the textbook by Hennessy and Patterson. Caching instructions and data is needed to help to reduce the average access latency as well as the memory bandwidth requirements. However, caching shared data causes a problem. This problem is called the cache coherence problem. Basically, it means if there are multiple cache copies of the same data, how do we ensure that all copies are the same, that all copies are coherent? Note that we distinguish between private data and shared data. Private data is data used by a single core. In this case, there is or should be no cache coherence problem, since there is only a single copy of the data. Shared data, on the other hand, is data used by multiple cores. All cores want to have their own copy of this data, and this causes the cache coherence problem. In general, shared memory architectures cache both shared and private data and do not distinguish between the two. Let me now illustrate the cache coherence problem. Here we have an SMP with 4 processes and their private caches. And in memory there is a data item D that has the value 70. Now processor P0 reads the value of D. Since D is not in its cache, it will incur a cache miss and fetch D from memory. Now processor P3 also reads D. D is also not in the private cache of D3, therefore it also fetches a D from memory into its private cache. Notice now that there are 3 copies of D. One in memory, one in the private cache of P0, and one in the private cache of P3. Now P3 writes a new value, let's say 24, to D. Let's assume we have write-back caches, so we write the new value only to the cache of P3. Now there are still 3 copies of D, but they are no longer coherent. They are no longer the same. So when P0 again reads D, it will read the old value 17 it finds in its local cache. This is clearly wrong since D has gotten a new value, 42, before. But why do we need cache coherence? Well, we need it to communicate in a shared memory system. To illustrate this, here we have a simple shared memory program containing 2 threads, T1 and T2. Both threads access 2 shared variables, A and flag, and initially, as indicated at the top, both A and flag are set to 0. Thread T1 first sets A and then sets flag, and thread T2 stays in an idle loop until the flag is set to 1. Then T2 prints the value of A. Clearly, it was the programmer's intention that this program should print the value 1, even though in a very difficult way. But consider now what may happen when this program is executed on this SMP. Let's assume thread T1 is executed on processor P0 and T2 on P1. Initially, flag is set to 0 in the central shared memory. First, processor P1 reads flag. Because it's not in its cache, it will fetch the flag from memory, test it, and observe that it is 0. So according to the program, it should stay in its loop. Then P0 writes the value 1 to flag. Depending on whether the cache is write back or write through, it will only write flag to cache or also to memory. Let's assume it's write back. So flag is only written to the cache of P0 as shown here. Now P1 again reads flag. Now it's a cache hit and P1 will read its own copy of the flag. So it will still observe the value and keep looping, keep spinning as illustrated by this circled arrow here. In fact, it will loop forever because without cache coherence, P1's cache copy of flag will never change. Before we look at solutions for the cache coherence problem, let's try to define what a coherent memory system actually is. A memory system is coherent if and only if all processes at any time have a consistent view of the last globally written value to each memory location. Actually, this definition contains two different aspects of memory system behavior. The first aspect, called coherence, defines what values can be returned by a read. It defines the memory behavior with respect to a single location. The second aspect, called consistency, determines when a written value will be returned by a read. It defines the memory behavior of reads and writes to different locations. Consistency will be covered in a separate lesson. Let's focus on coherence first. A memory system is coherent if it fulfills three properties. The first is that the program order or thread order must be preserved. This means that a read by a processor that follows a write by the same processor with no writes in between by another processor returns the value written. Obviously, we expect this to be true since it's also true in unicorns. The second property defines what it means to have a coherent view of memory. If a processor P writes X and then another processor P prime reads X, then the read will return the value written, provided the read and write are sufficiently separated in time. It doesn't specify how long separated in time, but just sufficiently. At a certain time, the write should become visible. Finally, the third property is called write serialization. It means that writes to the same memory location are observed by all processors in the same order. So if X first 100 is written to X and then 200, and then all processors should observe the change of X first to 100 and then to 200 and not in a different order. This concludes this lesson. Thank you for watching. In the next lesson I will describe different classes of cache coherence protocols. Stay tuned.